Chapter 14. Chapter 14 is about acid and bases. Let's talk about some of the characteristics of acids. Acids, they carry hydronium ion. They have sour taste like lemon. If you taste a lemon, you know how sour it is? That's an acid. They dissolve many metals, like this picture. Okay, this is a piece of metal in hydrochloric acid. Okay, and as you can see, it will dissolve the metal. And when you dip in a blue litmus paper in acidic solution, it will turns red. Then these are some of the characteristics of acid. And these are some of the examples of acids, like sulfuric acid is the first one. The second one is acetic acid. Third one is nitric acid, hydrochloric acid, and phosphoric acid. And as we've discussed in the past, all acids are in aqueous state. Bases, they carry hydroxide ions. They have a bitter taste. They feel slippery. If you've ever felt some cleaners, they're all bases. Okay, and you will see on your hand it will feel slippery, and when it will turn a red litmus paper blue. Okay, and these are some of the characteristics of bases. Then all the cleaning detergent that we use in the house, they are all bases. These are some of the bases. Okay, the first one is sodium hydroxide, the second one is potassium hydroxide, and the last one is ammonia. Okay, ammonia is the only base that does not carry hydroxide ion, but it's a weak base, and that's our only base, whereas NH4 plus is ammonium ion. Okay, now let's talk about a definition. It's an Arrhenius definition of acid and bases. Based on the definition of Arrhenius, acids contain hydrogen atom. Okay, and once they dissolve in water, they produce hydronium ion. Okay, then as you could see here, hydrochloric acid is a strong acid. Okay, this should be in aqueous state. Hydrochloric acid is a strong acid. Then it will undergo 100% ionization, which will produce hydronium ion and chloride ion. Also, to balance the hydrogen and the oxygen, then for every hydronium ion that we add a molecule of water in the opposite side. Then since I put hydronium ion on the product side, we do hydronium ion on the reactant side. Then, based on the Arrhenius definition of acid, hydrochloric is an acid. Why? First of all, it contains hydrogen ion, and second of all, it produces hydronium ion. Okay, then that's it. That's an acid. Also, based on the definition, they have hydroxide, and they form hydroxide ions. Then the sodium hydroxide is a strong base. Okay, Okay, let's put in parentheses, strong base. Okay, then it will undergo 100% ion dissociation, and this one has to be AQ, and it produces sodium ion and hydroxide ion. Then based on the definition, sodium hydroxide is a base because it contains hydroxide ion. Now, when we have strong acid reacts with a strong base, that reaction is a neutralization reaction, okay? Because the product is water. The pH of water is 7. And when the pH is 7, that means that solution is neutral. Okay, let's consider one strong acid and one strong base, like sodium hydroxide and hydrochloric acid. Okay, then whenever we have an acid reacts with the base, no matter the strength of your acid and base, your product is always aqueous salt and liquid water that we've discussed in previous chapters. Now, this equation is already balanced. We don't need to balance it. This is your balanced molecular equation. Now let's write the ionic form. Okay, then sodium hydroxide is a strong base. It will dissociate. Hydrochloric acid is a strong acid. It will ionize this completely. Sodium chloride is an ionic compound in aqueous state. It will separate. And water molecule. Instead of one water molecule, we will have two water molecules. Why? Because one is coming from the formation of hydronium ion, and the second one we already had it. Okay, that's why we have two water molecules. Now let's get rid of the spectator ions. Then sodium ion and chloride ion are our spectator ions. Then when you write the net ionic equation for this reaction, as you could see, hydroxide ion reacts with hydronium ion, and it produces two water molecules. Okay, then this equation that you see right here is the same equation as above. They're exactly the same equation. Okay, and as you can see here, when we have a strong acid react with a strong base, okay, we call that a neutralization process, because you will produce water and the pH of water is it's 7. Then when the pH of water is 7, that means it's a neutral pH. That's why it is called neutralization reaction. Okay, it has to be a strong acid with a strong base. Arrhenius definition had some problems. One of the problems was that if your base did not contain hydroxide ion, it could not explain it, because based on the definition of Arrhenius, bases, they carry hydroxide ion. Okay, but let's consider ammonia. Ammonia is a base, but it does not contain hydroxide ion. Then it fails in this particular example. Also, Arrhenius definition only works with aqueous solutions. Then if it would have been non-aqueous, it could not explain it. It could not figure out if it's acid or base. Okay? Then these were the two problems with Arrhenius definition. The first one, if the base did not contain hydroxide ion, okay, like ammonia. And the second one, if your solution was in non-aqueous state, it could not explain it. It could not differentiate between whether it's an acid or a base. That is why it was replaced by a more complex definition. It's a Bronsted-Lowry definition. Okay, then Bronsted-Lowry's definition is very complete. Then based on the Bronsted-Lowry's definition, acids, they donate protons, and bases, they accept proton. Okay. Then one more time, based on the Bronsted-Lowry definition, acids, they donate protons, which is either hydrogen ion or hydronium ion. It's the same thing. Our book refers to it as in hydronium ion. That's why we're going to stick to hydronium ion. Whereas bases, they accept proton. Then acid going to lose that proton, and the base going to gain that proton. Okay. And as it explained in the previous slide, it applies to wide range of acid-base phenomena, unlike the previous definition. Then let's do this example. Okay. Here is a reaction between hydrochloric acid with water, which produces hydronium ion and chloride ion. Okay. That's a simple reaction. And instead of gas, it's better to make it aqueous. Okay. Now, what happened here? Look at hydrochloric acid here, and look at chloride ion. Then it has lost the H. It has lost the proton. Then it has lost the H, and that's why hydrochloric acid has gone from HCl to Cl minus. Then since it has lost that proton, it's an acid. Now let's look at water here. In this particular example, water, it has 2 hydrogen, but here it has now 3 hydrogen. Then it has gained a proton. That's why here water is a base. Okay. So that's always how you will figure out when one species, which species is an acid, which one is a base. Look at the hydrogens. If that's one of the reactants losing the hydrogen, it's an acid. The second one that's gaining the hydrogen is a base. Then we always have an acid with a base. You cannot have 2 acids or 2 bases. Then one of the reactants going to lose the proton, the other one going to gain it. Okay, it's like redox reaction. One species going to lose the electron, the other one going to gain it. That's why we cannot have 2 acids or 2 bases. We always have an acid with a base reacting. Okay, here ammonia, if you look here, look at ammonia in this particular example, NH3. Okay, NH3, it has 3 hydrogens. Now look at the other side. It has 4 hydrogen. Okay, then it has 1 extra hydrogen. That's why it's a base. Remember, base accept proton. Now look at water. Water has 2 hydrogens. Now on this side, it only has 1 hydrogen. Then it's losing the proton. Okay, that's why it's an acid. Acid, they donate proton. Okay, then in this example, ammonia is a base because it goes from 3 hydrogen to 4 hydrogen, means 1 extra hydrogen. And water is an acid because it goes from 2 hydrogen with 1 hydrogen, okay, which is 1 less proton or hydrogen. That's why it will become an acid. Now, what are the conjugate acid and bases? Okay, in any acid-base reaction, in an acid-base reaction, as you all know, a base accepts a proton. Okay, a base gets a proton, then it becomes a conjugate acid. Okay, an acid, as we all know by now, they donate proton, then it becomes a conjugate base. Now look at this particular example. Sulfuric acid has 2 hydrogen on the reactant side. Now look at the product side. Instead of 2, it only has 1 hydrogen. Then it has 1 less hydrogen. Then it's donating its proton. That's why it's an acid. Now let's look at water. Water has 2 hydrogen on the reactant side. But look at the product side. It has 3 hydrogens. That means it has gained a proton. That's why water is base, whereas its pair becomes conjugate acid. Whereas sulfuric acid itself is an acid, whereas its pair on the product side becomes conjugate base. Now, let's talk about ionization reaction one more time. Then this is a reaction between a strong acid, hydrochloric acid, and a strong base, potassium hydroxide. And as I told you guys, regardless of the strength of acid and base, the product is always aqueous salt and liquid water. And this specific reaction, whenever we have a strong acid reacts with the strong base, it's a neutralization reaction because the pH of water is 7. This is the net ionic equation for any strong acid and base. Let's write it: net ionic equation for any strong acid with strong base. Okay, and because we have water is a neutral. The pH of water is 7. Okay, that's why when we have a strong acid reacts with a strong base, that type of reaction we call it neutralization reaction, because we end up with water and the pH of water is 7. Now let's talk about titration. Titration is a very, very important concept in chemistry. I'm going to go over a whole bunch of definition and then I will do some calculations. So what's titration? By definition, titration is a stoichiometry calculation involving acid and bases. Okay, that's what titration is. It's kind of follow the same type of stoichiometry calculation that we did, but it involves acid and bases. And when we have a titration, always one of the solution is the concentration is known, and the second one it's unknown. Okay, then for titration, usually one of the concentration of one of the reactants is known and the second one is unknown. That's why we do titration, in order to find the concentration of the unknown solution. When we are doing titration, usually a solution of known concentration is added to the solution of unknown concentration. Okay, then this is a typical titration setup. Okay, this is called a burette. And this is called Erlenmeyer flask. Okay. Why we are using Erlenmeyer flask? Why not using beaker? The reason is that when we add solutions from the burette into the flask, since if it did not have a tight neck, everything would go out. We will lose some of the drops. That's why we have this tight neck flask to prevent of loss of any of the droplets. Okay, we want to make sure every single drop get into the solution. Then what we have in the burette, we usually have a solution of known concentration, and in that Erlenmeyer flask, okay, we usually have solution of unknown concentration. One other thing that we use during titration is we use indicators. In addition to our acid base, we use indicator. It's very important to use indicator during titrations. Why? Because when we are doing titration, we are looking for changing color. Then imagine we are adding a clear colorless solution of a known concentration to a clear colorless solution of an unknown concentration. Okay, then let's write this down. Then that one is clear colorless. Okay, and the same thing with the solution that's inside the Erlenmeyer flask. It's clear and colorless. Then, as I told you guys, during titration, we deal with changing color. That's when it's important. Then when we are adding a clear colorless solution to another clear colorless solution, you will not see any changing color at all. That's why we use indicators. We have so many different indicators, but one of the more popular one that it's been always used is phenolphthalein. Okay. That's a very popular indicator that we use in any acid-base reaction. It's called phenolphthalein. Okay, then what happens is that phenolphthalein, it changes color at different pH. Okay, then if the pH is in acidic range, okay, or less than 7, the color is colorless. Okay, and colorless. And if the pH is in basic range, which is greater than 7, the color is pink. Right? That's why we'll be using phenolphthalein in this type of typical acid-base titrations. Phenolphthalein is one of the indicators. We have so many different indicators, but it's very popular. Okay, and it changes color at different pH. Then when it's in acidic pH, or the pH is less than 7, it's colorless. It has no color. When it's in basic pH, the color turns pink. Here is what I mean by acidic and basic. Okay, pH goes from 0 to 14, midpoint is at 7. Then if the pH is less than 7, it's acidic. If it's greater than 7, sorry about that, this one is wrong. The pH is less than 7. If it's greater than 7, it's basic. And when it's exactly at 7, right here, exactly at 7, it's neutral. Okay? Then when phenolphthalein is in acidic pH, that means pH is less than 7, this color is colorless. When it's in basic pH, that means the pH is greater than 7, is pink. And as I told you guys, phenolphthalein is a very popular indicator that we use in any acid-base titration. Now this is how titration works. Then what we have a burette and we have a burette. This is a burette. This is our Erlenmeyer flask. Like for example, what we have here, we have a base in the burette. Let me put a base in the burette. Let me change the color. Let's put it red. I have base here, and in the Erlenmeyer flask I have acid and I have indicator. Okay. Then as you could see here, right now, and we use phenolphthalein as an indicator. Okay. Then as you could see, the color of our acid solution is colorless. Also, you need to add about between 2 to 3 drops of indicator. You don't need to add any more than 2 to 3 drops. That's more than enough. Then what heats here, here we know the concentration of your base. It's known. Whereas the concentration of the acid, it's not known. We don't know it. That's why we are doing titration, to find the concentration of our acid solution. Then what happens here, we slowly are adding base into the Erlenmeyer flask or into our acidic solution. And while you are adding the base inside the Erlenmeyer flask, you need to swirl the flask the whole time in order to find a homogeneous solution. You want to make sure everything mixes. Titration reaction experiment lab requires a lot of patience. You cannot just do it and finish. You have to take your time, and you slowly have to add the solution from the burette into the solution inside the Erlenmeyer flask. And after every couple of drops, it's a good idea to mix the Erlenmeyer flask in order to get a homogeneous solution. Then at one point, after adding specific amount of base from the burette, you will see that the color of the indicator inside the Erlenmeyer flask has turned pink. What does that mean? That means this is, now we have the pH is greater than 7. Okay, then if I go back to my previous slide, oops, sorry about that. If I go back to the previous slide, then if the pH of the indicator is greater than 7, it's in basic phase. That's why it turns pink. And that's what happened. Okay, that means now in here I have basic solution. That's why the indicator has changed color. This point is called equivalent point, as you could see right here. Okay, that's an equivalent point. Equivalent point means the number of moles of acid is equal to number of moles of base. That's our equivalent point. That means we have the same number of acid and base. After you reach the equivalent point, you want to give it like about 30 seconds, and if the solution stayed pink, the color of the solution inside the LMFS stayed pink, you're gonna write the volume of base that you added. Okay, and here in the second picture, it's basically exactly what is happening. Here you have our acid with an indicator. Now we are slowly adding sodium hydroxide into the acid solution, and you will see after adding specific amount of base into the LMI flask, it's starting to change pink, and now at this point it has turned completely pink, which is the equivalent point. That means we have the same number of moles of acid and base, and we use the equivalent point to do our titration calculations. Okay, then one more time, going back to thinking about the picture, then at the start of the experiment, okay, we added base to the acid. Okay, then we did know the concentration of our base solution, but we did not know the concentration of our acid solution. Now, equivalent point, it's when the number of moles of hydroxide ion or the number of moles of your base is the same or equal to the number of moles of your acid. Okay, that's equivalent point. And as I told you guys, we use the equivalent point to do all our titration calculation. And as you could see in the picture that I showed you guys, the equivalent point is signaled by an indicator. Then phenolphthalein is a popular indicator that we use that changes color. Then it's pink in basic solution and it's colorless in acidic solution. Then if I go back, then it turned here, the color of the acid did not change. It is the color of the indicator that changed, that made the solution to be pink. Okay, and here, since we are adding base into the acid solution, that's why we have pink. That means here the pH of the solution is greater than 7. It's a basic environment. Okay. Then here one more time, once we reach the equivalence point, we wait about 30 seconds to make sure the color stays pink, and then you're gonna carefully measure the volume of the solution that you added from the burette. Okay, you're gonna read off the volume of the solution inside the burette. Then using the volume of the solution inside the burette, knowing how much that you use and knowing the concentration of the solution inside the burette, you could use stoichiometry to calculate the concentration of the acid. Now, one more definition, endpoint. Okay, endpoint means the solution inside the Erlenmeyer flask stays pink. When it stays pink for a long time, that means since we added hydroxide ion into, if I go back here, actually let's draw it. not that hard. Okay, I had base here, and I had my acid plus indicator. Okay, then when you reach the endpoint, what that means here is that the number of moles of hydroxide ion is greater than the number of moles of hydronium ion. Why is that? Because we are adding base into the acid. Okay, if it would have been reversed, that means you had acid in your, if you had acid in your burette and you had base in your Erlenmeyer flask, then at the end point, the number of moles of your hydronium ion would have been greater than the number of moles of hydroxide ion. Then in this particular example that I did here, the moles of base is greater than moles of acid. Okay, since I'm adding base into the acid. But let's look at this example. Okay, now what I have here, I have acid solution and I have base in here. Then at end point, for this particular problem, at the end point, the moles of acid is greater than moles of base. Okay, then basically you always have to look at what is inside the burette for the endpoint. Okay, then if you have acid at endpoint, the moles of acid is greater than base. If you have base in your burette at endpoint, the moles of base is greater than the moles of acid. Okay, always look at what it is in your base, in your burette. Okay, now let's do this problem. And in this example, we've done a titration, okay, of hydrochloric acid solution against sodium hydroxide. Okay, then what we do know the concentration and the volume of sodium hydroxide. That I do know. Okay, I also know the volume of hydrochloric acid. Now what we want to find out is the concentration of hydrochloric acid. Okay, that's what we're going to do. Then the first thing that you want to do is to write a balanced chemical equation. That's the very first thing. Then we have hydrochloric acid reacts with sodium hydroxide, which produces sodium chloride. It's any typical acid base, aqueous salt and liquid water. Okay, then if you look, this equation is already balanced. I don't need to balance it. Then I do know the volume of my base and the concentration. And I do know the volume of my acid. What I want to find out is the concentration of hydrochloric acid. That's what I'm trying to find out. Okay, then what we're gonna do first, let's draw our map. We're gonna find, since we do know the moles since we do know the concentration of sodium hydroxide, we do know the volume of sodium hydroxide, you could find the moles of sodium hydroxide. Then I'm going to convert the concentration of sodium hydroxide to the moles of sodium hydroxide. And then I'm going to use our balanced chemical equation to convert the moles of sodium hydroxide to the moles of hydrochloric acid. And then, knowing the volume of hydrochloric acid, I could easily find the concentration of hydrochloric acid. Okay, now let's set it up. I know the concentration. Okay, I want to find the mole. The moles of sodium hydroxide. Or what we could do, you could write it mole per liter. Then I'm going to set it up so that the volume going to cancel out. I will end up with moles. That way, 12.54. And you have to make sure that's in liter, not in milliliter. You have to convert it to liter. Okay, then here I converted the concentration of sodium hydroxide to the moles of sodium hydroxide. Now, I'm going to convert the moles of sodium hydroxide to the moles of hydrochloric acid, and based on this chemical equation, it's a 1-to-1 ratio. Then I'm going to set it up so much that the moles of sodium hydroxide going to cancel out, and I end up with the moles of hydrochloric acid. Okay. And the last one, I'm going to convert the moles of hydrochloric acid to the concentration of hydrochloric acid. Okay. I do know the volume of hydrochloric acid. Okay. Then it's just 1 over 10.00 times 10 to the power of -3 liter. Okay. Then here, again, make sure the volume is converted from milliliter to liter. Then if you do the calculation, okay, before doing a calculation, let's make sure everything's we did correctly. All right, here the liter is gonna go for sodium hydroxide. In the second one, the moles of sodium hydroxide gonna cancel out with the moles of sodium hydroxide, and what we will end up with is the moles over volume, or liter, which will be concentration, and that number will be let me write it down. Okay, then we're going to multiply 0.100 by 12.54 times 10 to the power of -3 divided by 10.00 times 10 to the power of -3. Then if you do the calculation, actually you will get exactly 0.125 molarity. Okay, and for the sake of sig, this number is 3 sig, that number is 4 sig, and the ones don't count, and the volume is 4 sig. Then between 3 and 4 we use 3. And on your calculator, since you get exactly 3 sig, just leave it as is. Then here, with the use of titration, we calculated the concentration of hydrochloric acid to be 0.125 molar, or mole per liter. Then one more time, just go over it. What I did here, we knew the concentration of sodium hydroxide. We did know the volume of sodium hydroxide. I also knew the volume of hydrochloric acid. What I had to find out was the concentration of hydrochloric acid. Then the first thing that I did, I wrote a balanced chemical equation. Then it's a reaction between an acid and a base. then no matter the strength, the product is always aqueous salt and liquid water. And once it's balanced, then what we're going to do, we're going to convert the concentration of sodium hydroxide to the moles of sodium hydroxide using the volume of sodium hydroxide. And then I converted the moles of sodium hydroxide to the moles of hydrochloric acid using this balanced chemical equation. And then last, I converted the moles of hydrochloric acid to the concentration of hydrochloric acid using the volume of hydrochloric acid. Then as you could see here, everything can nicely cancel out all the units, and I will end up with mole per liter. Okay, that here, this is the concentration of hydrochloric acid, which is the answer to the problem. Let's do one more problem. Then in this problem, what we have sulfuric acid that reacts with sodium hydroxide. What you need to calculate, the moles of sodium hydroxide. And these are the information that you do know. You know the volume and concentration of sulfuric acid. Then what we're going to do first is to write a balanced chemical equation. Then sulfuric acid reacts with sodium hydroxide. Oops. And it produces sodium sulfate and liquid water. Then to the balancing, you have to add a coefficient 2 in front of sodium hydroxide and water. Okay, now this equation is balanced. Now what do we know? We know the volume of sulfuric acid. We know the concentration of sulfuric acid. What we're going to find out is the moles of sodium hydroxide. That I don't know. Now, what is my roadmap? My roadmap is going to be to convert the concentration of sulfuric acid to the moles of sulfuric acid and then to the moles of sodium hydroxide. That's all I need to do. Okay. Alright, now let's set it up. Let's go with this color. Then the concentration of sulfuric acid is 0.500 mole per liter moles of sulfuric acid. Now I'm going to convert that to the moles of sulfuric acid. Okay, all I have to do is to multiply it by the volume, and it's already in liter. I don't have to do anything. Here we found the moles of sulfuric acid, and now the moles of sulfuric acid will be converted to the moles of sodium hydroxide, and based on the balanced chemical equation above, 2 moles of sodium hydroxide is proportional to 1 mole of sulfuric acid. Okay, now what we're gonna do, we're gonna take care of the units. Then the liter is gonna go here. Also, the moles of sulfuric acid gonna go, and we do end up with moles of sodium hydroxide. Then in this particular problem, we multiply 0.500 by 1.00 times 2, and if you do the calculation, you'll get exactly 1.00. Actually, on your calculator you get 1 moles of sodium hydroxide. That's you will get number 1. But then now let's take care of the sig fig. When we take care of the sig fig, 0.500 is 3 sig fig, 1.00 is 3 sig fig, and 2 and 1 is insignificant. Since your answer has to be 3 sig fig, that's why I'm going to put 0.00 in front of the 1 to make it 3 sig fig. Then before it was 1 sig fig, but once I added the 0.00, I made it 3 sig fig as well. Okay, and this is the answer. That's our answer. Okay, now we're gonna do one more problem. Then in this problem, there's going to be a reaction again between sodium hydroxide and sulfuric acid. What we know here, we know the concentration and the volume of sulfuric acid. What we want to find out is the volume of sodium hydroxide. Okay, and again, let's look what we have. You want to know the volume of sodium hydroxide, okay, knowing the volume and concentration of sulfuric acid. Then again, like every other time, what we had to do, let me put it lower. What we had to do is to find, the first thing that we have to do is to write a balanced chemical equation for this reaction. Okay, now let's do it. Okay, I'm gonna write it as imbalanced since I've already did that in the previous problem. Okay, then this is a balanced chemical equation for the above reaction. Okay, what do I know? I know the concentration of sulfuric acid, 7.5. I know the volume of sulfuric acid, and I know the concentration of sodium hydroxide. What do I want to find out? I want to find the volume. That's what I want to find out. Okay, let's do our roadmap. That's number 1. What I'm going to do, I'm going to convert the concentration of sulfuric acid, okay, to the moles of sulfuric acid based on the balanced chemical equation above. I'm going to convert the moles of sulfuric acid to the moles of sodium hydroxide, and then moles of sodium hydroxide to the volume of sodium hydroxide. Okay, that's what I'm going to do. Now let's set up our equation. And the concentration is 0.4 sulfuric acid okay, 0.225 liter. It's already the volume in liter. It's good, we don't need to do the conversion. Now it's here we found the moles of sulfuric acid. Now I'm going to convert that to the moles of sodium hydroxide based on the balanced chemical equation above. Then 1 sulfuric acid two moles of sodium hydroxide, and then I want to find I'm going to find the now that I know the moles of now that I know the moles of sodium hydroxide, I'm gonna convert that to find the concentration of sodium hydroxide. Okay, which will be 2.5 moles of sodium hydroxide. Okay, now let's do the math. Or before doing the math, let's take care of the units. Here, the moles of sulfuric acid gonna cancel out with the moles of sulfuric acid. The liter gonna cancel out here. And the moles of sodium hydroxide gonna cancel out with moles of sodium hydroxide, and I will end up with the volume of sodium hydroxide, which is going to be equal to 0.6304 liter. Once you have your number, you are going to take care of the sig fig. Let me use a different color, red. 0.175 is 3 sig fig. 0.225 is 3 sig fig. 2 moles of sodium hydroxide over 1 mole of sulfuric acid. 2 and 1s, they have unlimited number of sig fig. But 0.125 here is also 3 sig fig. Then between, they're all 3, then our answer has to be 3 sig fig. Okay? Now what we're going to do, I'm going to write the rounded number. It will be 0.630 liter. This is the volume of sodium hydroxide that you've been needed to completely neutralize sulfuric acid. Okay? Then one more time, just go over it quickly. Then what I did, I converted. So the first thing that I did was to write a balanced chemical equation for the reaction between sodium hydroxide and sulfuric acid. Once I have it set up, knowing the volume and the concentration of sulfuric acid, I want to convert these numbers to find the volume of sodium hydroxide. Then the first, we're going to convert the concentration of sulfuric acid to the moles of sulfuric acid. Okay, for that we need to know the volume of sulfuric acid. Then the moles of sulfuric acid will be converted to moles of sodium hydroxide using the balanced chemical equation. And then the moles of sodium hydroxide going to be converted to volume of sodium hydroxide using the concentration of sodium hydroxide. Okay, and that's the setup that I did, and this will be my answer, 0.630 liter. Now let's talk about acid-base strength. Okay, we have strong acid and bases. What do we mean by strong acid bases? Strong acids and bases, they undergo 100% ionization, as we have discussed in the past. Then if you look at this particular example, hydrochloric acid is a strong acid. That's why it will ionizes completely, and it produces hydronium ion and chloride ion. And for every hydronium ion that we add a molecule of water on the opposite side. Since hydrochloric acid is a strong acid, as you could see here, we have a single-sided arrow. Okay, then that's what we do for all strong acids. Since they undergo 100% ionization, what that means is that all the hydrochloric acid ionizes into hydronium ion and chloride ion. There will be no leftover. Okay, that's why we use a single-sided arrow. Okay, and the same thing with sodium hydroxide, as you can see in this picture. Sodium hydroxide is a strong base, and it will separate into sodium ion and hydroxide ion. Okay, again, since it's strong base, it will undergo 100% dissociation, and that's why I use a single-sided arrow. It's very important to know when to use a single or double-sided arrow. That's why pay attention. When we have strong acid and bases, we use single-sided arrow. Now let's talk about weak acid and weak bases. Unlike strong acid, strong bases, weak acid and weak bases, they undergo partial ionization. That means only about 1% or less will ionizes. Then if you look at this example, it's hydrofluoric acid, which produces hydronium ion and fluoride ion. Then since only about 1% produces these ions, and about 99% or more remains as the acid itself, that's why we use a double-sided arrow, as you could see in this picture. Then whenever we have weak acid, weak bases, we have to use double-sided arrow as they undergo partial ionization. And the same thing applies to bases. Okay, let's do ammonia. Remember, ammonia is the only base that does not contain hydroxide ion. Okay, that produces ammonium ion plus hydroxide ion. Okay, then since ammonia is a weak base, only about 1% of it ionizes, but about 99% remains as the ammonia itself. And it applies to some other weak bases, like for example aluminum hydroxide, which is a weak base. Then it produces aluminum ion plus hydroxide ion. Okay, and since aluminum hydroxide is a weak base, then we also have to use a double-sided arrow. That means only 1% separates, and about 99% remains as the base itself. Okay, then for strong acids, strong bases, since they undergo full ionization, as you could see in the previous slide, we use a one-sided arrow. Okay, whereas for weak acid, weak bases, they undergo partial ionization, we have to use a double-sided arrow, since most of the acid, our weak acid or weak base, remains intact. Also, it's one more thing to say. This is a template to write equations for ammonia or for compounds that has a similar chemical formula as ammonia. Okay, this is the template. It's good to know for future usage. Here is a list of our strong acids and strong bases, which you need to memorize, and everything else which is not part of the list, it's weak acid, weak bases. Okay, then strong acids, they undergo full ionization. Weak acids, they undergo partial ionization. Whenever we are writing reaction involving strong acids, it will only strong acid on its own. It will be a one-sided arrow. Whenever we are writing equations involving weak acids, we have to write a double-sided arrow. Okay. Then as you could see, like if we're going to talk about this specific one, okay, oops, sorry, sulfurous acid. As you can see here, sulfuric acid is a strong acid, whereas sulfurous acid is a weak acid. Make a note of that. Also, what does it mean by diprotic? it means it has 2 hydrogen. Same here. Whereas phosphoric acid, it has 3 hydrogens. That's why it's triprotic. Okay? It's like 3 protons. What is proton? Is hydrogen. And the same thing applies to weak bases. This is the list of your strong base, which you need to know. Most likely they are metals of group 1 when they react with hydroxide, and the rest is weak base. Okay, as you could see here. Okay, and these are all your strong bases. And when you're writing a reaction involving a strong base only, it's a one-sided arrow. But whereas for weak bases, it's a double-sided arrow, as you could see in all these examples right here. Okay, then this is basic ammonia and all its derivatives. And as I told you guys in the two previous slides, we are using this template to write a partial ionization reaction for ammonia and all its derivatives. Okay, this is the template, and as you could see, we've all used a double-sided arrow since it's a weak base. Then it's a good idea to know and memorize the template for ammonia and all of its derivatives. It used the same formula. All right, now let's do this problem. What we're gonna do here, we're gonna find the concentration of a hydronium ion. The first acid is hydrochloric acid. Then you know hydrochloric acid is a strong acid. Then it produces hydronium ion plus chloride ion. Okay, since it's a strong acid, I use the double-sided arrow. It produces hydronium ion, and for every hydronium ion, we add a molecule of water on the opposite side. Now, what is the concentration of hydronium ion? Hydrochloric acid is 1.5 molarity. Then what we're gonna do, we're gonna convert the concentration of hydrochloric acid to hydronium ion. As you can see, it's a 1-to-1 ratio. Okay, moles of hydrochloric acid times it's 1, the ratio is 1-to-1. 1 mole of that over 1 hydrochloric acid. That's why the moles of the concentration of hydronium ion will be the same as hydrochloric acid concentration, since it's a 1-to-1 ratio. Now, B, which is acetic acid. Acetic acid is a weak acid. Okay, the first thing that we're going to do is to write the balanced molecular equation. Then it produces hydronium ion and acetate ion. Okay. Now for every hydronium ion, we add a molecule of water on the opposite side. And since acetic acid is a weak acid, I use a double-sided arrow. Okay. Now, what's the concentration of acetic acid? 3.0 molarity. Okay. Then what we're going to do here, just like above, I'm going to convert the concentration of acetic acid to the concentration of hydroxide ion. Hydronium ion, my mistake. And based on the balance above equation, it's a 1-to-1 ratio. Okay, again, the concentration of hydronium ion is the same as the concentration of the acid, since it's a 1-to-1 ratio. Okay. Now, we have to do one other thing. What kind of an acid is acetic acid? Okay. Acetic acid is a weak acid. Since it's a weak acid, only about 1% ionizes into the hydronium ion and acetate ion, and about 99% stays as acetic acid. Even though I calculated here, the hydronium ion concentration is the same as acetic acid concentration, the thing is, since this only produces about 1% or less, we could say here that the hydronium ion concentration is less than 3 molarity. Okay, this would be the answer. Then if I go back to the first question, the first question was hydrochloric acid, which was a strong acid. That means 100% ionizes into hydronium ion and hydroxide ion. That's why when we dealing with strong acids, the hydronium ion concentration is exactly 1.5 molar. Okay, because 100% of it produces the ions, whereas for weak acids such as acetic acid, since it's only about 1% of it ionizes into the ion, that's why the concentration is less than 3 molar. Let's continue with one more problem. What we're going to do here is nitric acid. Okay, the nitric acid is a strong acid. The nitric acid produces hydronium ion and nitric ion, and since we have hydronium ion, we add a water molecule to balance out the oxygens and the hydrogens. And since it's a strong acid, we use a one-sided arrow. This is the equation for ionization of nitric acid. Okay, since it's a strong acid, we're going to use a one-sided arrow. Now what I'm going to do here, knowing the concentration of our nitric acid and using the balance above chemical equation, I convert the concentration of nitric acid to hydronium ion. And since it's a 1-to-1, okay, and since nitric acid is a strong acid, it means 100% of it undergoes ionization, and it will produce all these ions 100%. And that's why the concentration of hydronium ion is exactly equal to 2.5 molar. Okay. Now for the next example, it's for hydroxide ions. Okay. Now let's look at the first one. It's potassium hydroxide. Potassium hydroxide is a strong base, and it produces potassium ion and hydroxide ion. And since it's a strong base, we will use a one-sided arrow. As you can see here, I'm not adding any water molecules. We only add water molecules when we are adding hydronium ion. If you don't add hydronium ion, you don't need to add water molecules, because think about it, when you add it, you're going to mess up the chemical, you're going to mess up the balancing. Now we do know the concentration of potassium hydroxide. Then what I'm going to do here, I'm going to convert the concentration of potassium hydroxide to hydroxide ion, and as you can see, it's a 1-to-1 ratio. Okay, And since potassium hydroxide is a strong base, that means 100% of it dissociate into these ions. Okay, that's why the concentration of hydroxide ion is exactly equal to 2.25 molarity. Okay. Now let's do another one. Let's do methylamine. Okay, methylamine, or any base containing ammonia, it's a weak base, and it's all its derivatives. Remember? Then the first thing again we're gonna do is to write a balanced chemical equation. Sorry about it. Then it's gonna be CH3 and H2. Remember the template? I'm just following the template. And since it's a since it's a weak base, we are using a double-sided arrow. Now, what I'm going to do here, I'm going to convert the concentration of methylamine to hydroxide ion. And as you could see, it's a 1-to-1 ratio. Okay, now methylamine, it's a weak base. That's why only about 1% of it ionizes. The rest remains as the weak base, and therefore our hydroxide ion concentration will be less than 0.35 molarity. Okay, now let's do strontium hydroxide. Let's change the color. Strontium hydroxide is a strong base. Okay, it's part of the list. Then it produces strontium ion plus 2 hydroxide ion. And since it's strong, we use that one-sided arrow. Therefore, since it's a strong base, 100% of it dissociate into the ions. And as you can see here, again, I'm not adding any water because we're not adding any hydronium. Now what we're going to do here, we're going to convert the concentration of strontium hydroxide to hydroxide ion. And as you can see here, it's a 1-to-2 ratio. Okay, it's twice as much. Okay, and since strontium hydroxide is a strong base, it will undergo 100% dissociation, and because of that, the concentration of hydroxide ion is exactly equal to 0.050 molarity. Okay, that's the answer. Now, this one here, we talk about self-ionization of water. If you recall Bronsted-Lowry and Bronsted acid that we talked about, if you recall some of the examples, sometimes water acted as an acid, sometimes it acted as a base. That's why we call water amphoteric, because sometimes it acts as an acid, sometimes it acts as a base. Then in this particular example, hydrochloric acid, as you could see here, it's an acid. Why? Because if you look here to the chloride ion, what happens is that it's losing the hydrogen, or it's losing the proton. That's why it's an acid. And for water, if you look here, water in hydronium ion, it's gaining a proton. That's why it's a base. And because of that, hydronium ion will become conjugate acid, and chloride ion becomes a conjugate base. Then in this particular example, water is a base. Now let's do another one. Okay, now look here. Now let's figure out. Look at the ammonia. Ammonia is NH3 here, whereas on this side is NH4. It's getting a proton. Now it's a base. And here, ammonium ion is a conjugate acid. Now let's look at water. Water, it has 2 hydrogen, and here it only has 1. That's why it's an acid, and its pair is conjugate base. Then if you look at this particular example, let me do it with, okay, this particular example. Now water is acting as an acid. Self-ionization reaction of water. Okay. Then since water sometimes acts as an acid, sometimes acts as a base, that process is self-ionization of water. Then for pure water, that makes the hydronium and hydroxide ion concentrations to be very little. Okay. Then it's yield to hydronium ion and hydroxide ion concentrations. Okay. And because of that, for pure water, hydronium ion and hydroxide ion concentrations are the same, and it's so little, as you could see here, is 1 times 10 to the power of negative 7 molar. Okay, that's how small it is. Now, the ion product constant for water, which call it Kw. Okay, to calculate Kw, this is the equation. Over liquid water. Okay. Then for liquid, the ion constant for liquid is 1. Okay. Now, what is Kw? Then hydronium and hydroxide ion concentrations for water at 25 degrees Celsius is equal to 1 times 10 to the power of negative 7. Then we're going to plug in those numbers. Going to come here, and that makes the Kw of water to be 1.0 times 10 to the power of negative 14. Okay. And that works in neutral pH. Remember, water, pure water, its pH is 7. Okay. And that's why, if you think about the pH scale that I talked about, at pH of 7, hydronium and hydroxide ions have the same concentration, because it has to have it. If it would have been, either one would have been bigger than the other one, we do not have a pH 7. Okay, that's why whenever your hydronium ion and hydroxide ion concentration is the same, that's why the pH of the solution is 7. These are how we calculate hydronium and hydroxide ion concentration, knowing the Kw of water. Then these are the equation. It's been rewritten from this equation that I told you guys right here. That's what we use. Then you don't need to know any of these numbers or how it's driven. All you have to do is to be able to use these equations. Okay, and this equation will be provided to you. You don't need to memorize it. Then for in all of this equation, the Kw is known, as you could see here, is 1.0 times 10 to the power of negative 14. Okay, then knowing that number, if the hydronium ion concentration is given, you could calculate hydroxide ion concentration and vice versa. this is basically the pH values for different concentrations of either hydronium or hydroxide ion. Then let's do our pH scale one more time. It goes from 0 to 14, midpoint at 7. Okay. Then at the pH of 7, then as you could see here, it's an acidic pH. When we have acidic pH, that means your hydronium ion concentration is greater than hydroxide ion concentration because we have more acids. Okay, now let's do a basic pH. That's where the pH is greater than 7. It's a basic environment, and what that means is that the hydroxide ion concentration here is greater than hydronium ion concentration. Okay. Now, what about at pH 7? At pH of 7, it's a neutral pH. I'm going to write this down here since I'm running out of space. It's pH of 7. Then what happens here? Our hydronium ion concentration is equal to hydroxide ion concentration. Okay, and that's where all these numbers are from. Okay, then basically you don't need to memorize this table. Just know that pH scale goes from 0 to 14 if the pH is less than 7. If the pH is less than 7, it's an acidic pH. That's why hydronium ion concentration is greater than hydroxide ion concentration. If it's at 7, it's a neutral environment where hydronium and hydroxide ion concentrations are the same. And if the pH is greater than 7, it's a basic environment. And what happens is that hydroxide ion concentration is greater than hydronium ion concentration. And that's exactly what is explained in here. Okay, and let me put, it's a neutral pH. That's neutral. Now let's do these calculations. Okay, then we're going to use the formula to do the calculations. Okay, as I told you guys, you don't need to memorize the formula. You just have to be able to use them. Okay. Now, the hydronium ion concentration is given. You want to calculate the hydroxide ion concentration. Then we're going to use this equation. Okay, that's the equation that we are using. Okay, this is the equation. Okay, it's Kw divided by hydronium ion concentration, which is 7.5 times 10 to the power of negative 5 molar. Okay, now if you do the math, okay, the hydroxide ion concentration will be equal to 1.03333 times 10 to the power of negative 10 molar. Now we have to take care of the sig fig. And for sig fig, okay, that's a constant, 2 sig fig. We don't look at it. We look at that number given. It's 2 sig fig. That's why your answer has to be 2 sig fig. It's 2 sig fig. Okay. Then what we did here, we divided 1 times 10 to the power of negative 14 by 7.5 times 10 to the power of negative 5. And the final rounded answer is 1.3 times 10 to the power of negative 10 molar. This is our hydroxide ion concentration. Now we have to answer the question, if the solution is acidic, basic, or neutral. Okay, look at the concentration of hydronium and hydroxide ion. For hydroxide is 1.3 times 10 to the negative 10, and for hydronium ion is 7.5 times 10 to the power of negative 5. Which one is greater? Okay, this one is greater because hydroxide is 10 to the negative 10, hydronium is 10 to the negative 5. Okay, it's a bigger number. That makes the solution to be acidic. Okay, then what I did here, I used the equation and I calculated. I used the equation and sorry about that, let me change it to a color that you guys can see. Then I used the equation and I calculated the hydronium ion, hydroxide ion concentration. Then I compare the concentration of hydroxide ion with hydronium ion. Then as you can see here, hydronium ion has a higher concentration than hydroxide ion. Look at it, that's 10 to the power of negative 5, 10 to the power of negative 10. That's a lot more smaller. Then since hydronium ion concentration is larger, that's why the solution is acidic. Let's do another one. Now it's the reverse. Now the hydronium ion concentration is the one that we're gonna find out, which is 1.0 times 10 to the power of negative 14 divided by hydroxide. Okay, then if you do the math, that will be equal to 6.6667 times 10 to the power of negative 13 molar. Okay, now we have to take care of the sig fig like always. 2 sig fig, 1.0 times 10 to the power of negative 14 is a constant number. You don't look at it, just look at the given one. That's 2 sig fig. That's why your answer has to be 2 sig fig. That makes the question or the hydronium ion concentration to be 6.7 times 10 to the power of negative 13 molar. Now we want to find out the environment of the solution. Hydroxide and hydronium ions. What is the hydroxide ion concentration? It's 1.5 times 10 to the power of negative 2. And for hydronium ion, it's 6.7 times 10 to the power of negative 13. Now look, which one of the two is the larger? 10 to the negative 2 is a lot bigger than 10 to the negative 13. Okay, that makes hydroxide ion to be a lot more larger, and therefore that makes the environment to be basic. Okay, that's how we do it. Then just like the previous example, I used the given equation and calculated the concentration of hydronium ion, and then compare the concentration of hydronium ion with hydroxide ion. And as you could see here, 10 to the power of negative 2 for hydroxide ion is a lot larger than 10 to the power of negative 13 for hydronium ion. And since hydroxide ion concentration is larger, that's why the environment is basic. I've already talked about the pH scale many times. Just go quickly over it one more time. Then as you can see here, the pH scale goes from 0 to 14. Midpoint is at 7. Then if the pH is less than 7, it's an acidic pH. If it's greater than 7, it's a basic pH. And if it's exactly at 7, it's neutral. Okay. These are some of the foods or solutions that are kind of acidic, basic, or neutral, then lemons are very acidic, strawberries are acidic, tomatoes are acidic. Milk is almost as close as to neutral. And a lot of the cleaning agents that we use in the house to clean are basic. Okay, then this is basically the pH scale that you have to know about it, and you have to be able to talk about it. Also, for acids, the more closer that we get to 0 and 1, the solution becomes highly acidic. And for basic, the closer we get to 14, it becomes highly basic. Okay, therefore, as close as possible we get to pH of 7, which is neutral, that solutions become either less or weakly acidic or weakly basic. Then when we go to the end of the pH scale, which is either 1 or 14, our solution become either strongly acidic or strongly basic. And once we get close to 7, which is pH neutral, our solution is either weakly acidic or weakly basic. Again, this is what I've always talked about, and that's the pH value at different solutions. Then at acidic solution, the pH less than 7, that's why hydronium ion concentration is greater than hydroxide ion, and it's greater than 1 times 10 to the power of negative 7. At neutral pH, hydronium ion and hydroxide ion concentrations are equal, and to 1 times 10 to the power of negative 7. In basic pH, the pH is greater than 7, and hydronium ion concentration is less than 1 times 10 to the power of negative 7. This equation that you see right here, okay, is to calculate pH from hydronium ion concentration. It's the pH is equal to negative log of hydronium ion. Then on your calculator, what you have to do is to find the log, which is to the base of 10 for hydronium ion. Okay, that's how we do it. Okay, this equation. Let me add 2 more before I go. Let me add 2 more. Okay, then POH is equal to negative log of hydroxide ion, and therefore also pH plus POH is equal to 14. Okay, these are another 2 equations that's a good idea to know. Also, let me tell you one more thing. Sometimes I see a lot of students write this POH, or they say pH is equal to negative log of hydroxide ion. This is wrong. Okay, this is totally wrong. When we talk about pH, it has to be hydronium ion. If you want to talk about hydroxide ion, we are dealing with POH. Okay, just make a note of that. Then all these 3 equations will be again provided to you. You don't need to memorize it. This is another type of rewriting the pH scale, okay, in terms of concentration values. Now let's do this problem. Then what we're gonna do here, we're gonna calculate the pH and POH of the solution, knowing the hydronium ion concentration. Then the first thing that I want to do is to find the pH, okay? Since pH equal to negative log of hydronium ion is equal to negative log of 1.2 times 10 to the power of negative 5. Sorry about that. Okay. if you plug in this number into your calculator, okay, then just plug in the number and click on log. If you have your calculator has that, click on log and you get a number. It's a negative number. The negative times a negative, we have a negative here, becomes a positive number. Comes 4.9208. pH and pOH, they do not have a unit. Okay? They don't have a unit. They are unitless. Then don't put a unit in front of it. Now, one point here that's kind of confusing is the sig fig, which is totally different. Why? For the sig fig, look at the sig fig of this number. How many sig fig is that number? It's 2 sig fig. Okay? Now 2 sig fig becomes 2 decimal in pH. That number is 2 sig fig. That why it becomes 2 decimal. Okay? That's where the dotted line is. It becomes 2 decimal. Okay? Then sig fig goes to decimal. Alright? Then 1.2 is 2 sig fig. But when we are doing the sig fig for pH and pOH, the sig fig turns into decimal. Then 2 sig fig has to become 2 decimal. Okay? And that makes the pH of the solution to be 4.92. Then as you could see here, 2 sig fig became 2 decimal. This number is 2 decimal and 3 sig fig. Okay? Then make a note of it. 2 sig fig becomes 2 decimal. That's how we do the sig fig for pH calculations. Now, we do know the pH. Okay? Now that we know the pH, we could easily calculate pOH. Okay? Remember, pH plus pOH is equal to 14. Remember that? Okay? Then pOH will be 14 minus pH, which is 14 minus 4.92, which becomes 9.08. Then since we are subtracting, we go by decimal rule. That 14, it's a constant, we don't look at it. We only look at this. That's 2 decimal. And that's why your answer is 2 decimal. Okay? Then the pH of this solution is 4.92 and the pOH is 9.08. Let's do another problem. Now here, we do know the pH. We want to find out the hydronium and hydroxide ion concentrations. Okay, then what we're going to do for this particular example, we're going to use this equation to convert the pH to hydronium ion concentration. Okay, then on your calculator, you have to anti-logarithm of 8.50 or 10 to the power of negative 8.50. Okay, you could do that. 10 to the power of negative 8.50. It's just the same thing. Okay, then if you do that on your calculator, your hydronium ion concentration will be equal to 3.16228 times 10 to the power of negative 9 molar. Okay. Now, we have to think about the sig fig. Okay, remember in the previous example, the sig fig from hydronium ion becomes a decimal in pH. Now we're going vice versa. Okay, now this one is 2 decimal. Okay, it is 2 decimal. Now your sig fig gonna be 2 sig fig here. That's 2 sig fig. Okay, we're going the other way. In the previous example, we went from sig fig to decimal, then 2 sig fig for hydronium ion became 2 decimal for pH. Now we're going to go the other way. Then 2 decimal plates for the pH becomes 2 sig fig for hydronium ion. Okay, that's where the dotted line is going to go. And therefore, it is equal to 3.2 times 10 to the power of negative 9 molarity. Okay, this will be the hydronium ion concentration. Okay, now how do we do the hydroxide ion concentration? Then what we know is that hydronium ion concentration or we could use the equation, which is 1 times 10 to the power of negative 14 divided by hydronium ion concentration is equal to 1 times 10 to the power of negative 14 divided by 3.2 times 10 to the power of negative 9. Then if you do the math, you will get that number as 3.16228 times 10 to the power of negative 6 molar. Now for sig fig, this is easy. 2 sig fig. That's why your answer has to be 2 sig fig. Now the rounded number gonna be 3.2 times 10 to the power of negative 6 molar. Okay. Okay, that's hydronium and hydroxide ion concentration. The one thing that you have to really pay attention is the sig fig. Then let me go back to the previous problem. Then what happens is that when we are using hydronium ion to calculate pH, when we are dealing with sig fig, the 2 sig fig for the hydronium ion becomes 2 decimal for the pH, as you could see here. Okay. And here, I was subtracting the number. 14 is a constant. I don't care about it. It was just 2 decimal. The answer had to be 2 decimal. Now, if I go back to the next slide, I'm doing the opposite. We do know the pH. We're going to calculate hydronium ion concentration. Then on your calculator, you want to, when you plug in the number, you have to put negative 8.50. If you don't put negative 8.50 anti-log, what you will get, you'll get a huge number. Okay? If you get a huge number, it's wrong. You want to get a small number. That's why on your calculator, you're going to anti-log of negative 8.50. You have to do that. You have to transfer that negative to here before anti-logging 8.50. If you don't do it, you're going to get a huge number. Once you do it properly, it will be the negative anti-log. It would be the anti-log of negative 8.50. You will get this number for hydronium ion concentration. Now we are doing the opposite way. Then what happens is that now we're converting 2 decimal for the pH to 2 sig fig. That's why the answer has to be 2 sig fig. This is our hydronium ion concentration. Now I use this equation and I converted the hydronium ion concentration to hydroxide ion. Then that number we don't care about for the sigfig, it's a constant. Then this number is 2 sigfig. That's why your answer had to be 2 sigfig. The last topic I'm going to talk about on this chapter are buffers. By definition, buffer is a solution that resists to the pH changes. Okay? Then when your solution, basically when the solution becomes too acidic or too basic, we use the buffer to resist to the change of that pH. Okay? That's a definition of buffers. Okay? That the pH changes very little when acid or base is added. Basically, it resists to the changing of pH. Buffers contain a weak acid and its conjugate base. This pair makes a buffer. Then buffers, they resist to the changing pH. And buffer consists of a weak acid and its conjugate base. Then what happens is that the weak acid neutralizes the added base, and the conjugate base neutralizes the added acid. Then how they work? They work in a pair. Okay? Then it's a weak acid and its conjugate base. It has to be a weak acid and its conjugate base. All right? Then what the weak acid does, it neutralizes the base, and what the conjugate base does, it neutralizes the added acid. That's why they resist to the change in pH. With the use of this pair of buffers, they resist to the change in pH. Now on the next slide, that's the example and how it works. Then as you could see here we've added sodium hydroxide. Okay? Then what happens here, if you look at this picture, let me get this going. Look at this picture. Then here, it's the sodium hydroxide. Now look here, acetic acid is a weak acid. Then what happens here, as you could see in this picture, the acetic acid reacts with the sodium hydroxide. Look here, which is a base. And if I go back, to my previous slide, then weak acid neutralizes the base. Okay? Then as you can see here, the weak acid reacts with sodium hydroxide. Okay? And it produces sodium acetate. Okay? Now, this will be the conjugate base. Okay? That's our conjugate base. Then what does the conjugate base does? It neutralizes the added acid. Then if you look here, that's our conjugate base. Okay? And this one is weak acid. Acetic acid is a weak acid. And sodium acetate is the conjugate base. Okay. Then as you could see, acetic acid reacts with sodium hydroxide and it produces water and sodium acetate. Sodium acetate now is our conjugate base. Then our conjugate base reacts with the acid and it neutralizes it. Okay, then at the end, what do we have? We have acetic acid and sodium chloride. That's how it works. And if I'm going to talk about it on this picture right here, then here sodium ion is added. Then the weak acid, which is the acetic acid, gonna react with that sodium, then becomes a conjugate base. Okay, now that conjugate base, what's gonna happen is that it's gonna react with the acid. Okay, and it produces the weak acid and sodium chloride. That's how buffers work. These are some of the common buffers, and as you could see here, they're all weak acids and their conjugate base. These are all acetic acid, bicarbonate, dihydrogen phosphate, and hydrogen phosphate. They are all weak acid. And the second pair, or the other pair, is the conjugate base, such as acetate, carbonate, and etc. Okay. Then one more time, buffers, they resist the change in pH. They come in a pair, and that pair is a weak acid and its conjugate base. Then the weak acid neutralizes the base, and the conjugate base neutralizes the acid. That's why they resist to the changing pH. You don't need to know the buffers, the list of buffers. All you have to know is to be able to recognize that if the solution is a buffer or not. Just look for the pair. It has to be a weak acid and a conjugate base. If it is, then it's a buffer. If not, it's not a buffer. This is the end of chapter 14. Thank you for listening to the lecture.